So we come to the last presentation for today by Evan Preller, advised by Dr. Jiajun Xu, Investigation and Design of Additively Manufactured Microchannel Heat Exchangers with Different Cross-Section. Evan, are you ready to share your screen?
Yes, I'm here, Dr. Nish.
Okay, go ahead, please.
I just have confirmation that my screen is up.
Yes, it is.
Okay. Thank you for the introduction, Dr. Nietzsche. My title of my presentation changed a little bit. It's the investigation and design of additively manufactured microchannel heat exchangers using direct metal laser sintering. My name is Evan Preller. I'm an undergraduate working with the Center for Advanced Manufacturing and Applied Research at the UTC, CAMSTAR.
I don't know. It was
Oh.
He said it
Hello?
was good. Of course.
And I'm working under my advisors, Dr. Xu and Dr. Kabir Najafi. So moving on, just to a little introduction of what a lot of that title means. So microchannel heat exchangers have a wide range of applications. They're used in aerospace, automotive industries, power generation, industrial processes, refrigeration. Excuse me?
Sorry. Yeah, go ahead.
Okay. So the suitability of microchannel heat exchangers for these applications is a high volume heat flux and a relatively compact size. And the demand for thermal management solutions only grows with the increasing complexity and usage of electronic components. Essentially, we are trying to pack more and more electronic components into a lot of aspects of modern day life. And with that becomes thermal interference as those electronics are becoming in closer proximity. So thermal management solutions are only going to grow. They're not going to plateau. There's increased need for this constantly. So moving into some of the literature review, what we were looking at in terms of heat exchangers and specifically additively manufactured heat exchangers and their efficiency. We looked at this this paper, Hydrodynamic Performance of Additively Manufactured Mini Channels. What this was it was a heat exchanger, single channels, manufactured additively manufacturing. They're using a variety of cross-sectional shapes. And this paper kind of analyzed some inconsistencies they had between what was a developed model or a planned model with CAD and what the reality was in printing microchannels of this scale. So you can see in the illustration here on the right, there's some kind of discrepancies between what was the objective shape and what was the end result. And so what they were trying to do in this paper was analyzing hydrodynamic performance, and that has a lot to do with the friction factor that was going into these channels, because additively manufactured components often have a higher surface roughness than stuff that's traditionally manufactured. It has an effect on fluid flow. And what they found in this paper was that, maybe unsurprisingly, the microchannel with the largest wetted perimeter, that is the maximized contact surface between the flow and the channel walls, was the one with the highest friction factor. And they were much higher than laminar flows of smooth channels. Now, what they had done in this channel is that all the channels had a consistent cross-sectional area of 1 millimeter squared. But looking at the wetted perimeter, because it had the highest friction factor, we thought rather than have a consistent cross-sectional area, let's try and go for a consistent wetted perimeter. So because we're additively manufacturing this, we also needed to develop supports for what was going to be printed using the UDC printer. And a large part of that is the support structure that goes into preparing the piece for actual printing. And so this paper, the optimization of support structures for laser additive manufacturing, was very, very helpful in kind of determining what we could accomplish with support structure. because a big part of additive manufacturing is you're trying to balance what you're going to need to do for post-processing, that is removing these support structures from the finished piece, and kind of your printing time, the amount of material you're using. Less support obviously means less post-processing, but there's some drawbacks to the actual printing process. So going forward, some research questions that we developed based on this. What are the critical design considerations for additively manufactured microchannel heat exchangers? Do the manufacturing techniques contribute to deviations from the CAD models, and do these deviations affect the overall performance? That was the friction factor of the fluidic performance that we're looking at. And then what kind of support generation determines an accurate print? What role does the support geometry play in mitigating thermal deformation and leading to an actual successfully printed component? So the first step in this was looking at our dimensioning criteria for the microchannels. We were kind of initially given some constraints. One was based on the resolution of the EOS M280 printer, which is the metal 3D printer that's at the university. You kind of lose resolution below a certain dimension size, and that dimension size was about 400 to 450 microns. So anything below that, you're not really going to wind up with a coherent shape. It's just going to kind of be a blob. So that was a lower end of our dimension process. And then the higher end was 1,000 microns, and that was established by previous studies that made the designation between what is a mini channel and what is a microchannel being less than 1,000 microns. Beyond that, some geometric features of the semicircular channel would determine the measurement for the wetted perimeter. Essentially, the wetted perimeter for the semicircular was always going to be the largest. So we had to kind of play a little bit of a puzzle, trying to fit within this criterions of a lower range of 450 microns and an upper range of 1,000 microns, hit the same wetted perimeter for all different shapes. And this would lead to different hydraulic diameters, but as long as we're keeping the mass flow rate and the wetted perimeter the same, we were trying to maintain a constant Reynolds number. So as you can see, when we maintained a constant wetted perimeter across the shapes, we can attempt to maintain a constant Reynolds number across the different geometric shapes that we were working with. As I stated before, what was determining this was the semicircular dimensions. Essentially, they were the largest diameter, trying to fall below our 1,000 micron upper range and still have the rest of the shapes fall within the 400 to 1,000 microns. But we managed to develop 8 different shapes with the same constant wetted perimeter. And we developed several aspect ratios for the rectangular shapes and the trapezoidal shapes at regular or consistent intervals. So in the end of the day, what we came up with was 8 different microchannel heat exchangers utilizing 4 geometric shapes: circular, semicircular, rectangular, trapezoidal. These were all developed using the CAD modeling software Creo Parametric 6.0. We had a constant wetted perimeter for all 8 microchannels of 2,543 microns. We fell within our microchannel dimensions in terms of classified as a microchannel and also working within the resolution capabilities of the EOS M280 printer. And we had to maintain a regular channel spacing and our aspect ratios for the rectangular and trapezoidal shapes, as well as trying to get as many flow channels as possible across the face of the heat exchanger. And we wound up with 27 flow channels each across all 8 heat exchangers. So moving from our CAD geometry to our support generation and preparation for print, this goes back to the paper we were talking about by Lindicki. We were looking at basically 4 major factors that go into determining the support structure. And this was the Z offset, which is kind of like a little cap that sits on the top of the support structure that is separates the part itself that's being printed from the support structure that connects it to the build plate. The kind of top length of that support, this second illustration here from the top, the hatching density, that is how dense is the support structure going to be, and then whether or not we're using a sort of hybrid support structure, that is a variation between what is a block, which is kind of just like a straight line or a rectangular shape, and a cone, which is obviously a conical shape, and what kind of strength considerations would go into using both of those. So just going a little bit into direct metal laser sintering, if people are not familiar. The printer feed chamber, you can see in the illustration here on the right, is essentially a space or a volume with this kind of metallic powder, this atomized metallic powder. And this can be a variety of things. It can be aluminum, it could be titanium. In this case, we used a steel. And what happens is as the powder is kind of pushed up from the feeding chamber, it's swept across the build platform and an even deposition layer. And then it's hit with the laser from the printer, and that fuses the metal powder into the shape that you desire, to the CAD design that you've uploaded into the printer. And so with each successive layer, the powder bed will be raised, the build chamber will be lowered, and the roller, scraper, or recoater will put a new layer deposition of the powder over the build platform. And part of what's desirable about doing it in terms of direct metal laser sintering is these can be kind of milled and worked with the same as traditionally manufactured pieces. So they can be welded, they can be polished, they can be finished, and you can come up with some geometric shapes or novel shapes that you wouldn't necessarily be able to accomplish with regular or traditional manufacturing means. I have a little video here. Hopefully it'll play. Oh. Apparently not. But moving on. So as I said, the printer that we have at the university is the EOS M280 direct metal laser sintering system. It uses a laser diffused metallic alloy powder in layers. It's got a laser power of 200 to 400 watts, which is adjustable depending on what you're looking to use or what kind of components you're.
Evan, Evan, you're at 13 minutes.
Okay, wow. All right. So I'll move fast. We're using Miraging steel in this, which is MA1, which has an accuracy of plus or minus 50 microns. So what we found initially printing is that we had some errors in printing. We had interrupted prints and aborted prints because we had an insufficient support structure. Essentially, we were trying to limit the amount of support structure that would have to be removed post-processing. And what that was causing was, as thermal deformation hits the support structure, there's a lifting of the part from it. So this would interfere and come into contact with the recoater blade. So what happens is, as the recoater comes across, it's hitting these deformations. Essentially, the part itself isn't level, and it's interfering along the z-axis with the recoater blade as it tries to sweep a new layer deposition across. And a large part of that was what's known as the downskin offset effect, which is essentially that initial layer between the support structure and the part. Actually, molten powder leaks into the support structure. So you're left with kind of an uneven layer for the part to be built on. And it can affect how the recoater can deposit a fresh layer because it's constantly running into contact or obstructions. So although there were no successful prints of the heat exchangers thus far, we can analyze some of the prints that were partially printed. And we had two trapezoidal and the circular cross-sectional area as well. And you can see in the left-hand picture there that it maintains mostly its circular shape, but you can start to see the limitations in the resolution of the printer because you wind up with kind of a almost hexagonal perimeter there. as opposed to a purely circular one. But an analysis of this would lead to whether or not these deviations from the CAD model are really going to affect our friction factor or our hydrodynamic performance experiments. Same thing with both the trapezoidal heat exchangers. We can see the largest aspect ratio on the top and the smallest aspect ratio on the bottom here. That they're conforming mostly to the trapezoidal shape that we were looking for in the CAD design, but you can see some loss of resolution around the corners as it starts to kind of round off there. And with simulations and based on previous studies, we found that deviations in dimension can range between 3 to 84 microns, which 3 microns is obviously not a big deal, but if every dimension is off by 84 microns, then it's going to lead to a kind of inconsistent wetted perimeter. So we start to look at simulation of additive manufacturing, how that could maybe help us predict some of the problems that we ran into initially printing in terms of thermal deformation, how that's going to lead to recoater blade interference. On the left here are just some illustrations of different simulations using different types of software.
Evan, we're at 16 minutes now. Perhaps you could finish up.
Sure. So you can just see that the support structure can be estimated to see if there's any sort of thermal deformation, if there's going to be some sort of interference in the z-axis, or any sort of thermal deformation of the finished part. I'd like to acknowledge the CAMSTAR lab and my advisors, Dr. Shu and Dr. Kabir, and in particular the Lockheed Martin Fellowship Program and the opportunity it presents. Here's some references, and if anybody has any questions, if we still have time, I'd be happy to try and answer them.
Okay, maybe we have time for one question if there's one. Okay, I actually have one that's probably a bit longer. I'll follow up offline about your Reynolds numbers and things like that. But let's move on now to the last presentation of the event, which is going to Tewodros Mamo, being advised by Dr. Zhang, time series forecasting using deep learning. Tewodros, are you ready to go?
Yes, can you hear me now?
Yes, it's a little bit faint, but yeah, go ahead.